Okay, thank you. Very good. Good morning, Stockholm, or good afternoon, I should say, and good morning to those of you here in Europe. You are in the process of Chapter 2, finding all the typos that on assignment, knowing that eager to pressing that would not keep you fully engaged. I have another homework assignment I'm going to now share with you. And this homework assignment will be due again a week from today. So when you're currently working on is due next Tuesday, and the one I'm about to describe will be due next Thursday, January 30th, which is almost, but not quite the end of the month. And what I'd like you to do is work out some numerics on the divergence problem, including the effect of spring nonlinearity. We discussed that, right, last time. So let me walk through this homework, and we're going to share all these notes with you. So you're welcome to copy down what's on my notes. So you're going to get a copy anyway. So you might just want to look at it and sort of it. When you're free, not only this morning, you can ask questions by email. In fact, I like questions by email. Because if you ask a question by email, then I can share it with everyone. So everyone benefits. So let's go back to our equation of equilibrium. That's equation 1. This is the aerodynamic moment, which we'll elaborate on in the unintended. And then this is the nonlinear spring, which generates a structural moment, and they have to balance, right? Separate sides. And then the aerodynamic moment is normally, by convention, it's a matter of convention to do this, is separated into two parts: a moment about the central aerodynamic center, which does not depend on alpha. That's the important thing about the aerodynamic center. By definition, it's the point about which a moment, due to the pressure distribution on the circle, does not depend on any of that, plus the lift times the distance from the aerodynamic center to the point where the springs are fixed, otherwise known as the elastic axis. And then you can write that in conventional non-dimensional coefficient notation. So this is the dynamic pressure area of this simple wing. Record this non-dimensional moment coefficient about the aerodynamic center. Again, dynamic pressure, the area of the wings. E is the same E that appears here. And then this is the non-dimensional form of our aerodynamic lift. And we have a linear term, and we also inserted another term, recognizing that physically this coefficient normally is negative because the aerodynamic lift decreases as you get to a larger angle set. So if we use two of these equations together, we can get the final form, not the final form, but at least a more elaborate form of our equation of equilibrium. And now I claim, and this is something we'll do throughout the course in various contexts, it'll be nice to non-dimensionalize this equation, because if I non-dimensionalize it, I will reduce it to the most fundamental non-dimensional areas that appear in this system. And this is something we do, of course, for many mathematical models. So we non-dimensionalize it by dividing by k alpha, because alpha itself is non-dimensional, right? So if I divide by k alpha, I will make this a non-dimensional form. Now, why do I choose k alpha? Well, because I've done this before, and I have some insight into the problem. And if I were doing this for the first time, I might choose to do it a different way, and then discover after several tries that this is the better way to do it. So I give you the advantage of my experience in that respect. But mathematically, you could do it some other way, right? But physically, the spring stiffness is a very basic parameter in a sense, sort of a natural parameter to use to non-dimensionalize all these terms. So here's the non-dimensional form of the equation, and now we're going to write it more compactly on the next page. I pause briefly for questions. Okay, are you still with me? Stockholm, are you still with me? No. Good. Moving right along. That's page 1. Page 2. Okay, so you recall that we did a linear divergence analysis, right? And we identified the divergence dynamic pressure. So this is dimensional, right? So I'm going to use this in non-dimensionalized equations in an interesting and helpful way. So this is the divergence dynamic pressure determined by the linear theory, where I don't include the nonlinear spring and I don't include the nonlinearity near the end. These parameters are both non-dimensional, but the ratio is still non-dimensional, right? And since that ratio appears, rather than keeping writing the ratio, well, define this to be this symbol, there'll be a non-dimensional spring ratio. You know, the cubic stiffness is a linear stiffness, so I'll define it this way. And then this ratio naturally appears, and you can rewrite it, if you think about it for a moment, in terms of these parameters. And I'll call this by this symbol. And then I'm going to non-dimensionalize Q by QD. I can non-dimensionalize some other way. Non-dimensionalize the dynamic pressure by the divergence. The linear divergence dynamic pressure is a useful thing to do, right? Because when it's 1, I expect to see something interesting. If it's less than 1 behavior occurs that's greater than 1, some other behavior occurs. So using all of these non-dimensional parameters in a compact way, here's my equation again. Okay, now what I would like you to do for your homework is I would like you to make a plot of alpha versus Q. If I delete that term, what will happen is below Q delta, which is a non-dimensional Q, right? Below 1, alpha is the only possible solution to alpha equals 0, right? Alpha equals 0 is a possible solution to this equation. It's the only possible solution when I'm below the divergence dynamic pressure. But when I'm above the divergence dynamic pressure, there are actually 3 solutions because it's a cubic, right? One of them is alpha equals 0. But if I eliminate that, there's still 2 more solutions. And so I'd like you to plot that for both the case where I set this coefficient. Remember, this is the non-dimensional aerodynamic moment about the MAC. And typically, it is a pretty small number. And often in divergence analysis, people just collect it all together. But I'd like you to also plot it for 1, because for the value of 1, because it will give you some additional insight. So you can do that, and then tell me what it means physically, to the best of your knowledge and experience. Okay? That's the homework assignment. The next one. Is that clear? For the moment. Okay. So you have questions. Are there any questions right now? No? Okay. Feel free to shoot me an email when you start working on it. This is due Thursday, right? So I know you'll start working on it Wednesday night, at least. So if you send me now if you send it to me after midnight, I may not give a response. So at least send it earlier in the evening on Wednesday, preferably before Wednesday. Okay. Very good. Moving right along. The next thing we want to do is talk about reversal. Okay? And again, we can do that within the framework of a linear model or a nonlinear model. And I think I shared with you a draft of the paper by Professor Spring2020, right? Who's done the nonlinear case. Unfortunately, I can't find that as a homework problem because he's already done it. I guess I could have shielded you from that knowledge, but I decided not to. So we'll briefly talk about the linear case. I would encourage you to read Professor Spring2020's paper, because one of the reasons for taking this course, I hope, is that you can read the current literature. I mean, that's current literature. It's just another good journal, right? So by virtue of having some exposure to this course, hopefully you can read this paper with some understanding. So let's talk about reversal. Well, it's page 3. Let's talk about reversal. Reversal actually can take several forms, but 2 of them I'll mention in particular. One is, if we go back to our typical section with the spring, right? If we now add a control surface, which rotates through some angle delta, the purpose of the control surface, there's several reasons for the control surface, but one of the primary reasons is you want to increase the lift. Okay. I mentioned I think earlier, if I increase the lift on this system, I'll generally change the alpha, the twist on the spring, and it may be opposing, that effect may be opposing the desired effect of delta increasing the lift. In fact, there can be a condition where the lift, the total lift, due to both the spring rotation and the delta goes to zero. That's what we mean by reversal. Another more elaborate form is if I have a real airplane wing, we'll talk about a more realistic model in a moment, maybe toward the end of this class. If I have a wing with two control surfaces, I may want to roll the aircraft, which means I rotate this one down, this one up, right? And so you can have rolling reversal, where you have two control surfaces in opposite wings, and they act anti-symmetrically. But here we're going to keep it simple, right? We're just going to think of one wing or one airfoil. So for this case, we still have my minus k alpha, alpha equals 0. And since we're doing a linear analysis, I'm just having the linear spring. But Professor Bueno is that is not. Okay. Now, m of y is still MAC plus LE. And remember, the definition of MAC is the moment about the aerodynamic doesn't depend on alpha. But it could depend on delta. In fact, it generally would depend on delta. If I have a control surface and I rotate that control surface delta, I'll change the moment about the AC as well as about the other one. Also change the lift. I'm not changing the pressure distribution. And we haven't looked at the pressure distribution per se because we don't need to for our present purposes. So later on when we talk about aerodynamics, what we first do is determine the pressure distribution. And knowing the pressure distribution, we can determine the lift, the moment, we might. For the moment, we only need the moment, right? And the lift. Okay. So again, we're going to write MAC as QSC times CMAC. But whereas before, MAC was a constant, right? Just some number. Now, CMAC is some coefficient that we, by tradition, call dCMAC, d delta, times delta, right? It now depends on delta. And this is a linear aerodynamic model, right? So, like I said, some coefficient proportional to delta. We could also think of the sort of the second derivative with respect to delta times delta squared. I mean, you could think of a power series representation, right? If you want to. That's sort of what we did when we were looking at nonlinear theory, nonlinear aerodynamic theory before. So I've got equation 1, 2, 3, and the same thing is true of lift. Well, lift is going to be QS times CL, or writing the CL, which is the non-dimensional lift coefficient, writing it out in more detail now, we have dCL d alpha times alpha, right? So we're also going to have dCL with respect to delta times delta. And I'm going to write this, I'm going to use this equation up here if I may. Save myself from equation numbers. Oops. How about that? QSC DC MAC d delta times delta. Okay. This is equation 3. This is equation 4. Now with all those ingredients, I can write down an equation. Note that the number of equations is still just one. It's just one equation of equilibrium to determine alpha, given delta. So I'm thinking of somehow I have a control system which allows me to describe delta. In a more elaborate model, I would put another string between the control surface and the main airfoil surface to represent the stiffness of that connection. It turns out, within the framework of linear theory, that the reversal condition doesn't depend on that string. but that may not be, probably is not obvious to you at the moment. But I just throw that in as an extra cool tidbit. Okay, so let's combine all of this. So if we take all these equations and put them in one, what will we have? We will have QSC DCMAC d delta times delta. That's this term, plus E times QSC times DCL d alpha times alpha plus DCL d delta times delta. That's this term, minus K alpha times alpha is equal to 0. Right? So that's equation 5. Now, what can we do with this equation? Well, given delta, we can determine alpha, right? It's a linear equation, so that's not going to be too terribly difficult. So what I could do is I could take this equation, solve for alpha in terms of delta. It's going to be a linear relationship, right? Obviously, since it's a linear equation. Put that in the expression for lift, and determine the lift, the total lift, entirely in terms of delta having eliminated alpha. But we have a question in Durham, North Carolina. The question is, this one? Yeah. Oh, I see. You don't like that? I don't like that either. I just did that so you were paying attention. No, I got overly excited. I don't need an essay. There's no essay, right? Because this without the E is just a lift. 10 times E, right? Sorry about that. In the homework, I emphasize the desirability, the advantage of non-dimensionalizing equations. But there's one great advantage of dimensionalizing equations before you write them in dimensional form before you do them in non-dimensional form. And that is, if I looked at this dimensional equation and I checked the dimensions of the string, they should be all the same. And I actually see that wouldn't be true, and so I would know I have a mistake, right? But now I know at least dimensionally it's okay because this term and this term have the same dimensions, right? It's a length times an area times dynamic pressure times a non-dimensional quantity. Yeah. Thank you. All right. So, again, what I can do with this equation is solve for alpha in terms of delta, plug it in here and become whole, right? Now, that's interesting to do. I may actually do that at the home assignment sometime, or maybe in the following class. But I'm going to bypass that calculation in the following way. Remember, reversal by definition is when the lift is 0. So another way to do it is I can take advantage of it. I can set the lift to 0. That gives me an equation relating alpha and delta. And then I can put that in this equation. Okay? This term, by definition, is 0 because this is the lift, right? So if I'm only interested in L equals 0 and not the more general case of how L varies with delta in general, right? I can just look at the reversal condition. So let's do that. Recall L equals 0 at reversal. Well, if I'm below the reversal condition, and below will mean I'm at a smaller value of dynamic pressure, as it turns out, L will be positive. If delta is positive, L will be positive. Above the reversal condition, if delta is positive, L will be negative. The sign of the lift reverses. I rotate this down, thinking I'll get positive lift, and if the dynamic pressure is too high, I should get negative. That's not a disaster, but it could be disconcerting. And I certainly wouldn't want to operate the plane near the reversal condition because I have much authority, right? I wouldn't have much control. I'm rotating this control significant change on that. No? Stockholm, are you still there? Good. All right. So, we call L equals 0 and reversal. If that's true, then L equals 0, that implies that DCL d alpha alpha plus DCL d delta delta is 0, which implies that alpha is minus DCL. Okay. Yes, you have a question?
Yeah, you asked another question.
Okay, why do you question?
Can you explain why we have electrical zero? Is it about that?
To the microphone, maybe? Yeah, I'm not quite able to hear you.
Why do we have electrical zero diversion? I'm not able to get that.
Yeah, I have no idea. Why do we have what now?
Electrical zero diversion.
Oh, elliptical zero at reversal. Why do we have elliptical zero at reversal? Oh, why does it? Well, what we're doing is we're investigating under what conditions that can happen. And since you haven't done this analysis before, you may not realize that the lift could be 0. But what I'm saying is, I think there is a condition when the lift is 0, and we're about to find it. Okay? So we're saying, if the lift is 0, under what conditions will that happen? And it turns out there will be a critical value of dynamic pressure where the lift can be 0. Does that help?
So we are assuming that electrical zero for the calculation.
Are we assuming electrical zero? We are doing, for the purposes of at hand, we are going to ask the question, is there a condition under which the lift can be 0? And to find that from our mathematical model, we're going to set the lift to 0 and then find out under what conditions can that be true. And it turns out there is a certain dynamic pressure at which the lift can be 0, just as there was a certain dynamic pressure at which divergence could occur. Does that help? Okay. All right. Now, let me back up a little bit. Remember what I said before. Let's go back to equation 5. Equation 5 is an equation which says, you tell me what delta is, and I can compute alpha from this equation, right? Then I can take that delta and that alpha and put it in the equation for lift, and I'll have that expression for lift. And that's, give me a delta, and that's what the lift is. Then I would look at that equation and say, by the way, can the lift ever be 0? And the answer is yes. Okay, that's a little more elaborate algebraically, and I'm trying to avoid doing that. But you can do it in the quiet of your office or library or whatever. The point of view I'm taking is, okay, let's assume the lift can be 0, which will simplify the algebra, and then we'll determine under what conditions that might actually happen. Okay? I see some nodding of heads here in Durham. I can't see the nodding of the heads in Stockholm, but I hope your head is nodding too. Okay. So what we're going to do then is we're going to recall that by definition the lift is 0 at reversal, and then find out if that's possible. That turns out it's quite possible. Okay. If the lift is 0, then the sum of these two terms is 0, and therefore I can find alpha in terms of alpha. Okay. And now I'm going to call that equation 6. Now I'm going to put equation 6 into equation 5, and recognizing that by definition the lift is 0 at reversal, this term is 0, right? Because I know it. And so all I have left is only I have QSC DCMAC with the delta. Say DCL over the alpha. Where? Which equation are we looking at? Oh, I'm sorry. Thank you. I didn't complete that, did I? Thank you. DCL D alpha times alpha, right? Is that helpful? Delta. Oh, delta. I'm sorry. Thank you. Delta. Thank you. I'll get it right in a moment. Yeah, delta. Thank you. Yes. Yeah. Thank you. Okay. So I've got this term. This term is 0 because I asked that the lift be 0. And then this term is minus P alpha. And then there's another minus sign, minus DCL D delta over DCL D alpha, all times delta equals 0, right? That's equation 7. You're free to diligently write this down, but I'm not giving it to you. Okay, now let's look at the equation. Again, there are two possibilities. One would be that delta is 0. That's not a very interesting possibility, but that could happen. But what we're interested in is the case where delta is not 0, but somehow this equation can still be satisfied. Well, this equation can still be satisfied if the coefficients of the delta terms sum up to 0, right? Okay. Now, you have to keep track of the plus and minus signs. I've got a minus sign here. I've got a minus sign there. But, okay, and so that's plus and a plus, right? And now I'm going to solve this equation because I know what I want. I'm going to solve for the q, which will make this equation 0 when delta is not 0. So q, if I set this term on the other side, I'll have K alpha times this ratio. Oops, wrong ratio. Divided by SC, and now I'm deliberately going to write this, put the minus sign here because I put it on the other side, right? Minus DC MAC D delta. And I put the minus sign there because my aerodynamicist friend told me, she swore this is true, that when she used an aerodynamic theory to calculate DC MAC D delta, or she took a rigid airfoil and put the wind tunnel and measured it, that it turned out DC MAC D delta itself is not big enough. Because when I rotate this control surface down, I create a moment up here at the center. It's the moment this melts down, not melts up. So DC MAC D delta for a reasonable airfoil turns out to be a negative number, which means minus that is a positive. That's the key. So now what have I computed? Well, this is not just any old Q. This is a very special Q. This is the Q that makes the lift 0, because that's the way I assumed at the beginning of this exercise, right? So now I'm going to put an R here for reversal. Okay. So this is the dynamic pressure which reversal occurs. If I'm less than this dynamic pressure, the lift is positive. Okay. If I'm greater than this dynamic pressure, the lift is negative. And if we have done a more elaborate analysis, which I didn't do, right? And I had plotted and I determined Q. For a given Q, I determined L, right? That's what I would do by doing the more elaborate analysis, which I described to you, but wanted to avoid. Then at reversal, this lift is going to be 0. At low Q, it's going to be some positive number. At high Q, it's going to be some negative number, and it will go like this. That's what the whole curve is. And sometimes that whole curve is interesting, because people, rather than looking at reversal, you don't want to usually fly the airplane above reversal. Sometimes you do, if you have multiple control surfaces, and each one has their own reversal cue and you do it properly. But for a single control surface, you wouldn't want to fly above reversal. But even at lower values, you might lose enough lift effectiveness. The lift might decrease enough due to aeroelasticity that would not be a good thing. So, if Boeing or Airbus or Lockheed Martin or whoever would probably do this. I probably should have done the more elaborate analysis, or at least decided as a home. Well, we'll do that. You have done enough homework already. Later on, I'll remember this site. I will not forget. Okay, but we can compute the entire curve, right? But the entire curve would be solve that equation for alpha in terms of delta, substitute in the expression for lift. It wouldn't be a terrible thing. It's just more accurate. Okay. Now, one other thing I'm going to tell you, but again, I'll leave the analysis to you in the privacy of your office. I could define L sub rigid. What does that mean? That's the lift. It's just through the control surface, assuming that alpha is 0, right? Assuming that there's no cliff. Assuming that there's no elastic or aeroelastic effect, right? So that would be just QS DCL T delta times delta. This is the lift if alpha is 0. It turns out you can non-dimensionalize. you can compute the lift over lift rigid, right? Typically, this number is less than 1. Okay, and you could plot that versus Q. In fact, you can derive an analytical formula for our simple model, which is 1 minus Q over Q reversal divided by 1 minus Q over Q divergence. That's neat, right? But remember, buried in Q reversal and Q divergence are always parameters. K alpha is in there, E is in there, C is in there, S is in there. All those aerodynamic coefficients are in there, right? But nevertheless, if you define Q reversal and Q divergence, this is what? Which is neat. And so this curve is just a plot of this curve, right? Except that this curve, as I've drawn it, assumes that Q reversal is below Q divergence. Okay? Because if Q divergence is greater than Q reversal, then this thing will become negative and eventually will be infinity Q divergence. Conversely, if Q divergence is less than QR, this thing may actually go the other way. It will go up to infinity at Q equals Q divergence. So it matters which one's lower and which one's higher. So typically, people are interested in computing Q divergence and Q reversal, maybe even using some fairly simple model right away. Which one's really an issue? Sometimes, depends on the airplane design. Sometimes reversal is more of an issue. Sometimes divergence is more of an issue. So you want to be aware of both possibilities. And this formula, which only comes out of our simple model, guess what? Someone runs a fairly elaborate computer code and determines Q reversal and determines Q divergence, and then they just use this formula. Rather than keeping running that code, they just use this formula to make a first guess at how that's very So this is one of those little handy formulas that if you're a practicing airline person, you keep in your hip pocket. Oh yeah. Okay. I think that's all I want to tell you about reversal at the moment, although we may come back to that later on. We'll have it mathematical. Any questions about reversal? Okay. Stockholm, are you reasonably satisfied for the moment? You can say yes if you want to, or no.
Yeah.
Okay. Well, we've more or less exhausted our typical section, right? So do something that's more effective, something that would actually be useful if you want to do a wind tunnel test in the KTH wind tunnel or wind tunnel. So now something more like a domain, and we'll make a rectangular to start with, although the fact that it's rectangular isn't really essential. Do we have a question? Yes, Stockholm.
I wanted to ask you about the articulation road. Was there yet to this ratio actually versus the zero minus? Like, where is it helpful for us, this ratio?
I think that's a very interesting question, but I couldn't understand it.
If you would like to email it to me, Nanette, I can parse it here verbally to Dr. Dowell. We're struggling to hear you.
Yeah, I can hear you.
Okay.
They're going to email this.
Awesome.
Okay. We really anticipate your email. While we're waiting for that email, let me begin to describe the physical setup, and then we'll talk about the mathematical models. Now we're going to look at something that looks like a simple plate-like structure, actually more like a beam rod structure, because we're thinking of this dimension, which I'm going to tell as being large compared to this dimension, which I'm going to call C. So L is the span of the wing. C is the chord. And this is a continuous structure. So our simple model isn't going to quite do the trick, although as you'll see in a moment, the mathematical form at the end of the day, and the end of the day requires a bit of analysis, will look somewhat similar to what we had in our model of the spring. Okay. In fact, what you're really doing in some sense is just determining a more elaborate way of determining an effective spring constant. Okay. So what we need to do is we need to have a model which allows us. I think we have to have yes.
Can you move the book towards left? Because it's not visible. Half is not visible.
Okay, exactly. Okay. All right, good. We need a model which allows things to vary with y, with the distance along the spectrum. Later on, we'll need a model that varies with the distance along the spectrum. But if L is much larger than C, the primary variation of interest is along. Okay. So, how are we going to do that? Well, we could use Newton's second law to construct an equation motion. Okay. But I'm going to use the principle of virtual, which is a static version of Hamilton's function. Why am I going to do that? Well, I like it. But the other reason is that's what people do. And so, let me remind you of what the principle of virtual is. Principle of virtual work says basically minus del U plus del W equals 0. Well, that's fine, but what's U and what's W? U, and for that matter, what's del? L is not the control surface rotation. So there are only so many symbols. And yeah.
Where is the actual limit to lift at 0 alpha in a real case scenario? How do we interpret it?
Okay. You want to read that line again one more time?
Where is the actual limit to lift at 0 alpha? Step 1, lift versus lift at 0 alpha.
Okay. Okay.
Real case scenario, how do we interpret it?
Okay, fine. Let me repeat the question, and so we're all on the same page. I think the question is, what does it mean, or when is the lift 0? And the answer is the lift is not usually 0, but there is a central value of dynamic pressure at which it is 0, and that dynamic pressure is a Prague exercise. And therefore, a few moments ago, we tried to calculate that with some success. But in general, if I plot lift versus dynamic pressure, in general, the lift isn't 0. But there is a Q where it is 0. And below that, the lift is positive, meaning that if I rotate the control surface down, the lift is up. Whereas if I'm greater than the reversal condition, if I rotate the control surface down, the lift is actually down. And the reason it's down is because the twist itself has changed, right? And I rotate the control surface down, the twist is actually goes down. The twist itself is offsetting. The twist due to alpha is offsetting the twist due to delta. And there's a certain condition in which those two exactly balance, and that's the reversal condition. Does that help? Stockholm, does that help? No, maybe not.
Yes.
Oh. God bless you, sir. Thank you. Thank you. All right. Oh, this can easily be negative. It's just that that's designed. I don't want the lift to be in general. I want the lift to be positive. In fact, I don't even want the lift to decrease. Right? I don't want the lift to even go down. But it's inevitable because real airplane wings are elastic. They have flexibility. They twist. And almost invariably due to that twisting, if you ignore the flexibility of the wing, if you ignore aeroelastic effect. This is a static aeroelastic effect, right? This is the system has aerodynamic forces on it, and because of that, it's twisting. And because it's twisting, it's changing the aerodynamic forces. And the combination of that interaction is such that the lift is less than if you ignore the wing. If you ignore the aerodynamic elastic interaction. So people might design a real airplane. People might say, I want to design one to reach the reversal condition. I'm not willing to allow this thing to fly on that pressure. Or conversely, if I come to that pressure or a higher one, I have to stiffen up the wing, right? If I stiffen up the wing, it probably makes it heavier, which makes it less desirable in other ways. So there's a penalty to do that. Okay? Now, in reversal and divergence, we've covered all the physical lines. We've covered 99% of the physical effects of static aeroelasticity. But we've done it with an extremely simple model, both physical model and mathematical model, which is fine, because as we just discovered, even with a simple model, you have to think about what it really means, right? But at least with a simple model, we can work out the algebra and make some progress. But if I want to do an analysis for something that looks more like even a wind tunnel model, even a simple low-speed wind tunnel model, let alone an advanced supply, I need a more elaborate means of describing the behavior. And the next step up, not the final step, But the next step up is to look at something that looks like a wing with a large span and a small chord, and therefore can be treated as more or less something that still twists, but it twists in various ways along the spectrum. Okay? And it will turn out that the equation of motion now will be a differential equation, not just a integrated one. And I need a more powerful means of finding that differential equation. And there are various ways to do it, including do the second model. But I prefer to use principle of virtual work. And so does everyone else. Everyone who does this professionally. Okay, so again, U is the potential energy. And what is the potential? It's the potential energy of the spring in our rotor model, or the torsional elastic stiffness of our new model. And I'll write down the formula for it in a moment. W is work. And it's the work of exercise is the work done by the aerodynamic moment. And in particular, it's the work done by the aerodynamic moment. And delta, that's probably the most mysterious thing of all, is not the control protection. It's a virtual, this is a principle of virtual work, right? It should be really, I mean, we really should say it's a principle of virtual work plus virtual potential energy, but for shorthand we call it virtual work. Delta is the virtual and virtual work. And by virtual we mean we imagine it. Use your imagination sometimes. So this is the virtual change. Okay. Now, briefly, we're going to revisit our previous model to show you how it works in the case of the spring, right? And then we'll do something more elaborate. In the case of the spring, the potential energy of that torsional spring is 1/2 the spring constant times alpha squared. The work done by the aerodynamic moment, this is now not virtual here, this is actually actual work done. The work done is M times alpha. And so it's really, if you think about it, M sub y times d alpha. Why? Because M sub y itself depends on alpha, right? So we think of, you have to think of, I have a little bit of alpha, which creates a little bit of moment, which when multiplied by the change in alpha, it gives me a little bit of work, and then I have to add that all up, which adding up continuously is an error. Okay. The virtual work is the physical moment in this case times the virtual change in alpha. Some imagined change in alpha. And if you want to, you can think of it as delta alpha being really small, so that M sub y isn't changing very much, right? So when I compute for M sub y times a little bit, that's a little bit of a change in alpha. But then when I compute del u, the rules of the game are that I have to treat now the del operator like I would a differential operator in the calculus. So del u given this u is 1/2 k alpha times 2 alpha times del alpha. Right? Notice how conveniently the 2 is constant. It's really the other way around. When I compute this u I really compute U is I integrate from 0 to alpha, to K alpha, D alpha, to some nominal value. And then, of course, that gives me 1/2 K alpha, alpha nominal squared. So that's how it's always going to cancel when I do del, right? Because I constructed it that way in the beginning. And go ahead.
What is R from gold?
It's just a nominal value. I start out with 0 with no alpha at all, and I want to let alpha change from 0 up to some nominal value. And so that another way to do it is I can call this alpha, and I can call this a dummy integration variable. Just depending on the author and the text, they do it one way or another. Okay? Now, with all of this, and using this, do I get the same equation of motion I had before? Okay, believe that here the answer is yes. So, and before, this was using the proverbial cannon to shoot a mouse. But when I do even the next level of modeling, allow me to continuous twist, so alpha varies as a function of y, this is going to be much easier. Well, depends on how you feel about it, but most people would say this is a more efficient way of constructing the equation of function using principal virtual work. You still with me? Okay. All right. So now we're going to go our next level of knowledge. First of all, aerodynamic model. We are going to make a bold assumption, at least initially. If the span of the wing is much larger than the force, then each section, each span-wise section of the wing can be treated as though it were the same as a two-dimensional airfoil. Aerodynamics is called a strip theory, at least in English. I don't know what they call it in Russian and French. But in English they call it strip theory because you're looking at each span-wise strip as though it's an independent two-dimensional airfoil. Which means we can use the same aerodynamic model we had before, except the moment now is the moment per unit span. Okay? So our work, well, our moment, I'm going to call it M sub y, but now I'm going to call it strip theory. Rather than having Q times the area, I'm now going to have just Q times C times DCL D alpha times alpha. And I'm not allowing my control surface yet, but we can do that later if you like. Okay. But now, this has the dimensions of length, whereas before it had a dimension of area. So this is the moment per unit span, right? That's important. Because now when I construct the virtual work, I want to take the moment per unit span multiplied by del alpha and integrate over the span from 0 to L. Right? This is the total work done by all the moments acting all along the span and integrated over the span. Right? Okay. Now I was told by a reliable structural engineer, okay, U is equal to 1/2, and you'll not be surprised that's 1/2, right? Times the integral from 0 to L times Gj, I'll tell you about Gj in a moment, the alpha y squared. You shouldn't be surprised by the square because potential energies according to linear models always are quadratic for deformation, dy. And Gj is the torsional stiffness. is the shear modulus of the material pressure. It turns out to be the usual potential for an isotopic material is E over 2 times 1 plus nu, where this is the normal bending modulus and nu is the Poisson's ratio. It's a number, right? It's a material property. As the dimensions of pressure, force per unit area. I never remember what G is. I was at the computer if I remember what E is. E is 10 to the 7th pounds per square inch. And I think it's something else in Pascals. I think it's a factor of 6. I don't know if I might refer to Pascal. I just think that. Well, you can look it up. It's a number. It's the shear modulus of the material, and you say, look at the shear modulus of aluminum and tap your cell phone, it'll tell you. But E is Young's modulus. This is Young's modulus. Yeah. This is sometimes it's called Young's modulus, sometimes it's called the bending modulus as opposed to the shear modulus. J is a geometrical property. If we have a rectangular cross section of a wing, rectangular cross section with a certain thickness and a certain chord, it's 1/3 the chord times the thickness, which is usually denoted by H, because we like to have reserved the symbol for time. Q, where C is the chord, H is the thickness. If you have a different kind of shapes, I mean, people get confused to find what J is. You have structural units. You can also measure it if you have a physical model. But this is a handy formula to remember because, again, it's not a rectangular cross section, but you can sort of approximate by rectangular cross section, which they give you the right order. Okay. So now let's compute del U. That's important, right? In order to get our equation of equilibrium, we need to know del W, and we need to know del U. Right? So let's compute del U. Del U, again, we're going to treat U and alpha as though we're dealing mainly with the calculus in terms of del U. So this is going to be 1/2 is del U. We're going to fill the L of Gj times d alpha dy times del of d alpha dy d1. There's a 2 here. It's conveniently cancelled. 1/2 that. And so now I have an expression for del W, and I have an expression for del U, and I'm about halfway there. Okay, I'm about halfway there. I have to do 2 more things. First of all, this del alpha, this virtual change, is anything I want it to be. Okay. And therefore, the equation of equilibrium, which I'm about to find, has to be valid whatever del alpha. And it's going to be a little bit mathematically like what we've been dealing with. We're going to have something times del alpha in this case. We don't want del alpha to be 0, but otherwise it could be anything like. Therefore, we're going to have 2 terms, all of which multiply del alpha, and we want that equal to 0, and we want that statement to be true, and therefore the coefficient of del alpha must be 0. And that's going to give us our equation of equilibrium. There's only one little hitch. I've got in the expression for virtual work, I have del alpha. Here I don't have a del alpha. I have del of d alpha dy. But not just here. I can use one of the 2 tricks I remember about integrals to convert this into a del alpha. And that trick is integration by parts. I'm going to integrate this by parts. So when you apply this method typically, whether it's a principle of virtual work or later in the dynamic context of the Hamilton's principle, where we have integrals with respect to time and space. We'll have to integrate by parts with respect to time and space. Typically, we're going to do integration by parts, convert these things into del. And let's do that. Allow me to take a few extra minutes today. I'm going to integrate this by parts, and if I do that, I get Gj d alpha dy times del alpha evaluated at the limits. And there's always a minus sign when I integrate by parts, right? And then I have a minus sign d0 to L, the derivative with respect to y of Gj d alpha dy times del alpha dy. That's what I get by integration by parts. Note two things. At this point, I'm allowing Gj itself to depend on y. Why? Because the thickness might change along the span of the line. The chord might change, right? Why not? They do, right? So we should allow for that. The other thing is I have this tail term. Well, this tail term is giving me different information. That's what I'm telling you. I'm going to end up with a differential equation that governs the behavior of alpha. This tail term shows me what the boundary conditions are for the differential equation. Okay. Now, you might try to reason the boundary conditions by thinking physically, and that's fine. That's a good thing to do. But the nice thing about principal virtual work is it tells you what they are. In fact, it tells you the only thing they can be. Because consistent with a certain representation of potential energy, the principle of virtual work tells you what the determining equation is. It also tells you what the correct boundary conditions are. Because there are occasions known in the literature, famous occasions or examples, where people use the wrong combination of equation of motion, in this case, equation of equilibrium, and the boundary conditions. Right? This method ensures that you are at least consistent. Once you write down potential energy and once you write down virtual work, it's just a matter of following the mathematical stages. And you're guaranteed, assuming you do the algebra, you get the right answer. Okay. All right. So let's put this all together. We have minus del U plus del W equals 0. And we can write, what does that mean? If we write it all together, taking this expression for del U and this expression for del W, we're going to have the integral from 0 to L of Q C dCl d alpha times alpha. That's from del W. And it'll also be multiplied by del alpha in a moment. I'm going to stay with it. So they have this other term which also gets multiplied by del alpha. But it's minus del U, and here's minus sign, here's a plus sign, plus d dy of Gj d alpha dy all multiplied by del alpha dy. So I'm taking care of this term, I'm taking care of this term, and then I have minus Gj d alpha dy times del alpha evaluated at the two limits. That's equal to 0. So now I'm done for the moment writing the question. But let me give you the final interpretation of this equation. And then we'll begin again on Tuesday and go on from there. Del alpha is arbitrary. I don't want it to be 0. And I want this whole equation to balance. So the thing that multiplies del alpha for all points between 0 and L must be 0. That gives me a differential equation. Okay. This whole statement still must be true right at the endpoint, y equals 0 and L. Therefore, each of these two terms, there are two terms, right? And this tail term, so-called, must be 0. Now, it depends on, and now I have to think a little bit physically, because if I have a wing which is clamped at this end. Here's my point. I'm clamped at this end. Then alpha's got to be 0. Therefore, I'm not allowed to imagine any value of alpha other than 0. Therefore, at this end, alpha must be 0. At the free end, at the tip of the wing, del alpha can be anything, including 0. Therefore, the thing that multiplies in must be 0. So at the free end, GJD alpha D1 must be 0, which you can interpret physically as a shear strain, actually. And it's not surprising that at free end you would have a shear strain. So that's it. Now, when we solve this differential equation, such as this boundary condition, we're going to find divergence again. Right? And if we added a control surface, which we could do, which would add another term to the virtual work, we could do reversal again. But now, the calculation will be more elaborate, because now I have to solve the differential equation. And if I allowed for things to vary not only in the y direction, but the x direction, I would end up with an even more elaborate equation, which would be a difference equation as a function of x and y. The good news there is people have developed computer codes to do that. So what we're doing is we're using this math model to see how they work. So when you run your computer code from your industry, you'll realize what's inside the code, at least to some degree. Okay? I'm sorry to keep you for a few extra minutes, but I'm not going to charge you any more tuition today, so it's okay. We'll see you on Tuesday. Cell phone, did you have any further questions before we finish? I'll take the answer. Well, look at this.